So there's one little bit of linear algebra that I want to refresh you on, and hopefully all of you remember this, and I can wake you up in the middle of the night and you'll be able to rattle it off. But these are just some useful things about dot product. So dot product is a fundamental operation that we're going to use in building all of these similarity functions, right? So it's a way to measure similarity between two vectors A and B. So if I have a vector A, which has d dimensions, a1, a2 through ad. I have a vector b, which also has d different numbers representing it. A dot product is you just take the first element in vector A multiplied by the first element in vector B. I take the second multiplied by the second, and you add them all up. Right. So algebraically, really simple. Usually we're going to write it as either a dot b or a transpose b, just shorthand. But really what it is it's a sum over all the terms in our dimensions, and usually our dimensions are words, so I is going to be a particular word. So it's a sum over all the words, the weight that document A assigns to the word I times the weight that document B assigns to the word I. So that's what it looks like algebraically. Geometrically, and that's quite important, geometrically you can think of a dot product as a projection operator. So if vector B is unit length, you can actually interpret the dot product as the length of a projection that vector A casts onto the line in which the vector B lives, right? So think of a shadow, a perpendicular, if there's a sum there, that's the length of the shadow that vector A would cast onto the line of vector B. And a couple more observations. I guess if vectors, this quantity, this length of the shadow, it's going to be highest if A and B point to the same direction, right? You should be able to convince yourself of that. So the bigger you make the angle between the two vectors, the shorter the shadow is going to be. The shadow is shortest when the vectors are perpendicular to each other. So if they're orthogonal, then there is no shadow. So the dot product is going to have value 0. And I guess we're talking about text, so what do those things mean? When you have perpendicular vectors, that means that two documents or two pieces of text have no words in common. That's the only way you can have perpendicular vectors. Now that's not strictly speaking true if we allow negative components, but it turns out that in the vectors that we'll be dealing with, all the AIs and BIs are going to be strictly non-negative. So they're going to be either 0 or positive. And if that's the case, the only way you can have perpendicular vectors, if the only way you can have it if there is no overlap between the words in vector A and vector B, so they don't overlap at all. And if the vectors point in the same direction, again, what that means is they have exactly the same words in exactly the same proportions. That's the only way to have vectors pointing in the same direction, and that will give you the highest possible value for a dot product. So we have some intuition there. I guess from geometry, you should also remember that a dot product, there is another way to express it, right? It's just the length of vector A times the length of vector B multiplied by the cosine of the angle between the two vectors. So when we're computing a dot product between A and B, what we're actually doing is we're measuring the angle. Now, if the document lengths are not normalized, then it's not exactly the angle. But if they are normalized, then dot product is really the same thing, the same exact thing as the cosine of the angle between the two vectors. So a dot product is also related to the Euclidean distance between the endpoints of the two vectors. And that is also hopefully painfully obvious to you, right? So if I take Euclidean distance between A and B and just play around with the algebra a little bit, I can massage it to the form where I have the square of the length of vector A plus the square of the length of vector B plus minus twice the dot product of A and B. And if the vectors are unit length, which we'll have a lot of the time, then there is a direct inverse relationship between a dot product and the Euclidean length. So 1 minus the dot product is just half of the square of the Euclidean distance between the endpoint of B and the endpoint of A. So they're the same thing. And I guess if the lengths are 1, then it's also the same thing as the cosine of the angle. So all three are intimately related. Right? So if I ever ask you what is the difference between the cosine and the Euclidean distance, now you know that there isn't, as long as the vectors are normalized to unit length. They're the same thing. Okay, so it's also worth remembering that these are related to these can be related to your logical operations, such as set intersections, right? So, and if I happen to have binary vectors are the same thing as sets, right? So imagine I have a vocabulary of 3 words, and now each value of the vector is restricted to either be 0 or 1, right? 1 means that the word I occurs in the document. 0 means that the word I doesn't occur in the document. So a binary vector is the same thing as set membership, as a function that indicates which words are members of the set and which ones aren't. And if you have binary vectors, then a dot product is really the same thing as the set intersection operation. Right? So the dot product, I take A1 times B1, and think about what this means. A1 is 1 if and only if the word 1 occurs in document A. B1 is 1 if and only if it occurs in document B. So A1 times B1 tells you, is the word 1, is the first word present in both document A and in document B. And then when you add it up over the whole vocabulary, you get just the size of the intersection of the two sets, or the number of words that you have in the overlap between the two documents. So they're all closely related to each other.